I was talking with my wife earlier this afternoon, and I was talking about, before I was ever a ham, I knew there was Dayton Hamvention. I knew about ham radio and I knew about Dayton. And it was so, in my mind, it was so exotic and so far away and so impossible that I could ever be at such a place that it was, I might as well have dreamed of flapping my arms and flying to the moon. It was beyond the realm of possibility. And especially when I was a baby ham and you know, just this would be impossible. This is now our 4th year here. And so take a moment and appreciate being here, because this is something a lot of hams never get to experience. And just, you know, just take a moment and go, wow, I'm at Dayton. And for some of you, you're at Dayton for the 5th time or the 10th time or whatever. I mean, that's pretty amazing. It's pretty amazing. And by the way, thank you for making it possible for us to be here. Okay, let's get started on this thing. I said I was showing you this for a reason, and we'll get to it in the presentation. I'm Michael Burnette, I'm AF7KB, and I'm the author of the popular license training programs called the Fast Track series. I'm also the author of this little book on ham radio propagation, which is, of course, our topic today. So what is propagation? Well, my take on it is propagation is everything that happens to your signal between the transmitting antenna and the receiving antenna. Different things happen based on where the signal starts its journey, what's in the path of that journey, and what frequency the signal is. Maybe a more useful question than what is propagation, though, might be, what is propagating? In other words, what is the nature of that radio signal? Understanding that is one of the keys to understanding propagation. And of course, the answer turns out to be anything but straightforward. Radio signals and light are dual-natured. In fact, they are so confoundingly strange that language sort of breaks down as we try to describe them. I mean, we could say radio signals consist of particles and/or they consist of waves. We can do experiments that absolutely prove that radio signals are waves and not particles. And we can do experiments that absolutely prove that they are just the opposite. Now, before we go too much further, just in case there are any physics professors here, are there? Let me say right up front that I have taken some liberties with some of the physics involved in what we're addressing today, in order to serve the multiple purposes of time intelligibility and minimum math. So, radio signals are waves. They cannot be particles. Radio signals are particles. They cannot be waves. We're not going to resolve this paradox here today. There's no treasure down that hole. Instead, since we can interpret a radio signal as either a wave or as a particle, well, that's at our convenience. So we can just use that to further our understanding of propagation. The good news, though, is that you can think of any mode of propagation as either a wave phenomenon or a particle phenomenon, whichever makes the most sense for you regarding that phenomenon. Now, in the book, we cover over a dozen distinct modes of propagation and several subsets of those modes, and we're not going to cover all those today because we're in Dayton with 10,000 things to do, and by the way, dinner's waiting. Instead, see, I understand. We'll cover a handful of modes, and along the way, we'll try and note whether we can apply the particle model or the wave model to better understand those modes. So we'll start down here on the ground and we work our way up to the sky. Let's start with ground wave propagation. This one's a favorite of the top benders, those folks who like 160 meters. A ground wave leaves the transmitting antenna, and at least for a while, it goes across country following the curvature of the Earth. Now, how does this happen? Don't radio waves travel in a straight line like light? How can it do that? Well, spoiler alert, the answer here in the real world is radio waves almost never travel in a straight line. We learn early on in our radio education that radio waves travel at the speed of light, which is true as far as it goes. It's just that the speed of light isn't always, well, it isn't always the speed of light. At least it's not 300 million meters per second. That's the speed of light in a vacuum. In the air, the speed of light and of radio waves a little bit slower. And through the Earth, it is considerably slower. So to create a ground wave, we need an antenna, and a vertical is generally the superior choice here, and we need ground radials. Think of that system as inducing a wave that's partially in the air and partially in the Earth. That Earth part is what those radials are for. The part of the wave passing through the Earth is moving just a bit slower than the part passing through the air. And as it moves along, the whole thing sort of leans over as it goes, and it sticks close to the ground. It's something like when you're riding on an escalator and your hand is traveling a little bit faster than your feet. And if you were a kid and you rode an escalator, you did this experiment on the escalator, right? Well, that radio wave's doing that same thing. I mentioned that top benders, those folks on 160 meters, are very interested in ground waves. They can provide excellent propagation in the near range, say out to 50 miles or so. Ground wave propagation is superbly dependable. It doesn't fade. It doesn't disappear if you get a building between you and the transmitter. And the ground waves don't stop working just because the sunspots are having a bad day or a bad decade. So how do we create ground waves? Well, commercial AM stations, that's the world I came out of, operating down there below our 160 meter band, spend lots of money to create ground waves. They do that by having massive ground radial systems under their vertical antennas. Typically, they'll have 120 quarter wave ground radials strung out around the base of their quarter wave vertical antenna. That is a lot of copper. And if you've priced copper lately, you know you're talking about an expensive proposition. A more economical solution for us in the ham radio world is the inverted L antenna with a horizontal element, a vertical element, and ground radials that are more along the lines of what most of us are used to, which is kind of minimal. Ground waves depend on ground conductivity. The more of it, the better. And so if you want to create a great ground wave, you need to have the foresight to live in a part of the country with great ground conductivity. This is actually the official FCC map of ground conductivity. That's it. If you can read the tiny little numbers on there, you will see that Oklahoma and Kansas and a lot of that center section of the US has pretty fantastic ground conductivity. Most of the West Coast, not so much. Now, I'm from Seattle, and you might think, wow, up in Washington, I hear that's the soggiest place in the world. They must have great ground conductivity. No, we do not. We have no minerals left in our ground because it all washed away centuries ago. So our ground conductivity is terrible. You want to choose the right operating frequency too, if you want to create ground waves. It's really unlikely that you'll create much of a ground wave at frequencies above, call it 5 megahertz. And even if you do create one, it's not going to go very far. So 160 meters, yes. 80 meters, maybe 60 meters, not totally impossible. 40 meters, not going to happen. So now let's touch on VHF, UHF propagation. We all learn about line of sight propagation when we study for our technician license, but the test never mentions the fact that down here in reality, pure line of sight is pretty rare. It's really rare. I'd be so bold as to say that most of the time, there's no such thing as line of sight propagation. For most of us, the predominant form of propagation that we're using in the VHF and UHF bands is not line of sight, but it's terrestrial scatter. Our signal is being affected by goodness knows how many buildings, cars, trucks, mountains, and who knows what else in our way to the receiver. So Carrie and I live on the back side of a hill relative to our club's repeater. And on paper, there's no way our signal can hit that repeater. This is a radio path study of it. That's us over on the right side and the repeater over on the left side. You'll notice there's a lot of very solid stuff between us and the repeater. And yet, we're on the club net just about every week, and Carrie hosts her weekly YL net and is part of the rotating lineup of net control operators, all done from our house. Our best guess is that we're either knife edge diffracting over that mountain, which is not real likely, or more likely we're bouncing off the side of a mountain that's about 20 or so miles north of our house that has a clear shot to our house and to the repeater. In this sort of propagation, we can think of our signal as a stream of particles, ping pong balls, ping-ponging semi-randomly around the area. Doesn't do us much good to think of these as waves. But if you start thinking of particles and you think, what could I bounce that particle off of, all of a sudden propagation possibilities open up. Now, another way our UHF, VHF signals get to places beyond the line of sight is tropospheric scatter. Our atmosphere is usually not perfectly homogeneous, okay? Think of a cup of coffee into which you've just poured some cream, but you haven't stirred it yet. That's kind of what our atmosphere would look like if you could see it. There are discontinuities in the atmosphere, and each of those discontinuities presents an opportunity for refraction. See, that's where refraction happens, is at a discontinuity, a sudden change of density. Think of refraction as a bending of the signal's path. I mean, look, that pencil is straight above the water, it's straight below the water, and yet at that change of density, there's diffraction happening. Bend that signal enough times through enough diffraction zones, and even if it's just a little bit each time, it might get pointed back toward Earth and make it far over the horizon. Tropospheric scatter, or troposcatter to its fans, doesn't often work in our favor though. Typically it's just a source of multipath. Like a terrestrial version of sporadic E though, every now and then it opens up, much to the delight of VHF, UHF, and even microwave DXers. I think those forms of scatter are best understood with the particle model, ping pong ball model. Let's look at something that's probably best understood with the wave model. Now, this isn't really a propagation mode, but it's something that can at times rather drastically affect even a very ordinary works on paper sort of signal path. It is called the Fresnel zone. It's named for this happy French fellow, Augustin Jean Fresnel. So here's a nice, clean, open path between two nice, high, open mountains. This is exactly what we look for when we want to do linked repeaters, right? It's a happy signal path. How often does this happen in the real world? Not very often. It seems like there's almost always obstructions of some sort, and yet somehow radio communications work day in and day out. So the question is, How bad is bad when it comes to signal paths? There's actually a reasonably simple formula to model the zone between the transmitter and the receiver that needs to be fairly free of obstructions to produce a useful signal at the receiver. That zone is called the Fresnel zone. Now, what you're looking at there, these little gray lines, if you can see them, sort of an oval around the words Fresnel zone, that's not the radiation pattern of the transmitter. That's the shape, roughly, of the Fresnel zone. So if something reflective impinges on that Fresnel zone, signal quality degrades. I'll tell you, in reality, this is only half of that story, but hang in there, we'll get to part 2. In this picture, we've added a mountain in the middle. That mountain is going to seriously impede the transmission, even though we could stand on mountain A and use our binoculars and see mountain B absolutely perfectly. Straight shot, and yet that lump poking into the Fresnel zone is going to impede the signal. Simply put, that mountain in the middle is going to create an interference pattern, and that's going to cancel part or even all of our signal. Now, we can calculate the radius of the Fresnel zone at any point along the signal with a reasonably simple formula. It is radius equals 1/2 of the square root of the wavelength times d, which is the distance from the transmitter or from the receiver, whichever is shorter. The rule of thumb is that 60% of the Fresnel zone radius needs to be clear at any given point along the zone. So for a practical number, the full formula would look like radius equals 1/2 of the square root of the wavelength times the distance times 0.6. Now here's how this might apply in the real world. First, I do realize that you are unlikely to be calculating the Fresnel zone between your car and your club's repeater. It's not very practical. That path is either going to work or it's not. But let's say we want to build a permanent auxiliary transmitter that will send signals to a repeater up on top of a local mountain. We do a path study on one of several computer models that'll do that sort of thing. And we end up with something like this. This is actually a real path in my neck of the woods. Everything here looks great right up until we get to point A. That's about 12 kilometers from the receiver. Right there, we have 20 meters of clearance over the top of that peak. So, here's the question. What frequency do we need to use to put a solid signal up to the receiver? Well, now there's a social complication. Our club member, Bob, good old Bob, has been a ham approximately since they invented lightning. And somewhere in his garage, he's pretty sure he has a perfectly fine, if slightly dusty, Heathkit 2-meter radio. And while he's reluctant to part with this potentially priceless antique, his wife would be very pleased indeed if the club would accept his generous donation to use this in the auxiliary station. So, should we take him up on his generous offer? Let's check the numbers. We do radius equals 1/2 times 2 meters, that's the wavelength, times 12,000 meters, that's the distance, times 0.6, and we find out we need 47 meters of clearance over the top of that peak. We have 20 meters. That won't work unless we build a taller tower on one end or the other. Sorry, Mrs. Bob. The Heathkit's staying in the garage. Now, I have had personal and rather stressful experience with this phenomenon. I was working at a commercial FM station in San Diego, California, and we were moving the studios from one downtown building to another. So there's our signal path, right from downtown San Diego to some insanely expensive real estate right above La Jolla, California. And that's where our transmitter was. Well, it turned out that the top of another building was just poking its big hairy toe into our signal path, just enough to totally disrupt our microwave hop up to that transmitter. The boss was not happy. Well, another section of tower and some very hasty construction, strictly to code, and with all necessary permits, I assure you, probably, we were back in business. Now, I told you I'd get to the other half of the story about the Fresnel zone, and this is it. The interference patterns created by impingements aren't necessarily destructive. They can also be constructive and actually improve your signal, leading to an even stronger signal. Given all the measurements, we always suspected that we hadn't actually managed to raise that antenna enough to clear that building, but in fact had just raised it enough to change from destructive to constructive. We'll never know because they wouldn't let us get on top of the tower or on top of their building and take measurements, but kind of suspect that's it. Anyway, it worked and the boss didn't throw us off the building, so that was good. So that gets us to what I guess is the big topic when it comes to propagation, and that is the ionosphere. To be an active HF operator is to have a, let's say, a relationship with the ionosphere. Sometimes a pretty emotional relationship too, especially over the past decade or so. The ionosphere is the second highest part of Earth's atmosphere. The top layer is the exosphere, and really that's just the transition to deep space. Not a lot of interest for us up in the exosphere. The ionosphere starts about 30 miles above the ground and continues way on out to about 1,000 miles above the ground, although not much is happening at that altitude for us. The air is very, very thin up there. The molecules are far apart. And compared to down here. And they are farther apart to the tune of anywhere from about 100,000 times more distant from each other to over 1,000,000 times more distant. Now, in this ionosphere area, 4 large complex forces come together to create the ionosphere. They are solar radiation, the Earth's geomagnetic field, terrestrial weather, and the ionosphere's own weather patterns. All right, let's start with solar radiation. The sun is constantly bombarding us and the rest of the solar system with radiation. In the case of the ionosphere, the relevant radiation for us is the ultraviolet and X-ray frequencies. The solar wind also has its effects on the ionosphere, as well as the occasional blasts of high-energy particles from solar storms. Then there's the Earth's magnetic field. So this is the way most of us got taught Earth's magnetic field in school. It's very nice, very symmetrical, nice and tidy, very easy to understand. It doesn't even remotely resemble reality. The Earth's geomagnetic field is a constantly shifting and wobbling thing. The result, probably, we're not sure, but probably of what is basically a giant sloppy electrical generator in the center of the Earth. So this is a model of the real geomagnetic field. It was built by a supercomputer. As the Earth's solid iron core sloshes and rotates relative to the surrounding molten magma, well, we know what happens when magnets move past wires, right? Past any conductor. We get electrical fields and then we get magnetic fields. In this case, it's magnetism that tends to move around a lot. It practically ties itself in knots. When you see the aurora, they're tracing those moving magnetic lines of force. The magnetic lines of force also get knocked around by solar storms. All this tangling and untangling affects our ionosphere and our propagation. Terrestrial weather can affect the ionosphere, both with massive air movements down below, temperature changes underneath, and we think by pumping ions up into the ionosphere from the tops of thunderstorms. This is looking suspiciously like it might be one cause of sporadic E. Then there's ionospheric weather. It is truly weird. So ionospheric weather consists mostly of ferociously fast and strange winds. So down here on Earth, when the wind blows out of the north, the wind blows out of the north, and that's pretty much it. If you set up your little sailboat with the sail hanging out like this, you're gonna head for the south. You would be very surprised if your sailboat turned around and headed north. That's not the way it is in the ionosphere. Things are different there because the ionosphere consists of matter that's called plasma. In plasma, we can have a neutral wind, an ion wind, and an electron wind, all going in different directions at the same time in the same place. That's hard to even imagine. To put it mildly, this complicates things. So 4 semi-random forces interacting in a semi-random way do not add up to a system whose behavior is easily predicted, nor easily understood. Now, before we got started, I had a video playing of this desk toy, one of these deals. That's a version of a physics problem that's called the two-pendulum problem. It's a demonstration of chaos theory. There is no mathematical way to predict what that inner ring will do, what its, say, next 10 moves will be. 2 pendulums on a cheap, simple desk toy about a foot wide. 4 forces in the ionosphere, which covers the whole Earth and goes from, 30 miles to 1,000 miles. 4 forces, all semi-random. I hope that I've left you with at least a suspicion about the infallibility of propagation forecasts. See, nobody can predict propagation between your house and some point on Earth accurately, especially not more than about an hour in advance. So, if I leave you with anything, stop believing those propagation forecasts that say poor affair. I know you all check them if you're a DXer, but they can't tell you anything about the conditions between your house and where you want to reach. Now, happily, the dominant force of all of these is the sun, and we have a reasonably good handle on its effects, so we can generate at least some modestly useful predictions, mostly with some really vintage software known as VHF. I would just caution you, though, even if the so-called official prediction looks like this, that doesn't necessarily make it so for you. Really, propagation predictions have almost universally been for poor propagation for over a decade now. We're just starting to see some good propagation in the last few months. But for a decade, it was 10 meters was a wasteland. I never heard a good signal on 10 meters for all that time. I heard nothing but static. Suddenly, one day, someone is talking to me on 10 meters. Whoa, what is this? It was bad. And yet, so far as I know, the ARRL kept sending out DXCC awards all that time. Somebody was getting some propagation somewhere. So, what's going on up there anyway? As that ultraviolet and X-ray radiation comes bombing in from the sun, it knocks electrons in the air molecules out of their orbits and out, essentially, into free space. What was a space of neutral charge has now become a space of not neutral charge. The free electron is carrying a negative charge, and that atom that it left behind is carrying a positive charge. But for our purposes today, we don't care about the atom. The stuff we're interested in, the refraction of radio signals, gets done by those free electrons wandering around looking for an atom. The nighttime ionosphere is different from the daytime ionosphere. Of course, in reality, the ionosphere is staying the same and we're rotating underneath it, but that's how we talk about it. The part of the ionosphere in the Earth's shadow is, of course, getting a lot less solar radiation than the part facing the sun. In fact, that whole lower part of the ionosphere on the right side doesn't have much going on in the way of free electrons at all, which turns out to be really good news for us. The lowest layer is what we call the D layer. When Edward Appleton first started researching the ionosphere, he discovered there was a region at a fairly consistent height above ground that would return electromagnetic waves. See, so he called it the E layer for short. He just needed some shorthand for his notebook. Well, later we discovered more layers, and by that time it was the E layer, and so the one that was lower was the D layer, and the one that was higher was the F layer. So the letters really don't mean anything, and there is no A, B, or C layer either. There's just D, E, and F. F1 and F2 blend into one layer on the night side. Now, those layers' boundaries are constantly shifting, and they're defined by the rate of change in free electron density versus altitude, and by their behavior in regard to radio waves. So as you go up, the electron density doesn't change in a straight line. It stair steps up, and where those stair steps happen, that's where the layers are. The D layer disappears at night, leaving us for a little while around sunset and sunrise with the E layer, and then as the night wears on, we get the F layer. Now, why is it that sometimes 20 meters works at night and sometimes it doesn't? Well, that has to do mostly with levels of solar activity. And the easiest indicator we have of solar activity is the presence of sunspots. Simply put, more sunspots equals better propagation. So, understand, sunspots don't do anything to propagation. They're just an indicator that the sun is more active. That's what does things to propagation. So the sun isn't always the same brightness. Seems like it to us, but turns out not. For reasons we really do not understand, solar activity, and thus sunspots, and good HF propagation follow a 22-year cycle, giving us peaks every 11 years, or not. Sometimes the solar maximum is a dud, like the last one. Sometimes the solar maximum doesn't show up at all. During the Maunder minimum, back there around 1645 to 1715, nobody was getting any good HF propagation at all. It was terrible. I remember. Regarding all this, nobody knows the mechanisms that are behind this. There are many mysteries about our ionosphere and our sun that we have not yet solved. To understand what's happening to our radio signals and ionospheric propagation, I think it's useful to use our particle model of radio waves, if that makes any sense. To get a radio signal refracted, we need what you might call the Goldilocks combination of atmospheric density and solar radiation. So imagine a photon from our antenna that's blasting up to the ionosphere. One of three things is going to happen to that photon. One, your signal shoots right through the ionosphere, never to be heard from by anyone on Earth again. But it's out there in space somewhere. Two, your signal gets refracted back to Earth. and you're in a QSL. 3, your signal gets absorbed by the ionosphere and it never goes anywhere else ever. Let's say you're transmitting on 20 meters. For our little fantasy, that photon coming out of your antenna is exactly 20 meters wide, okay? It gets up to the ionosphere and it encounters a bunch of free electrons that are, say, an average of 19 meters apart. Well, again, this is fiction. All of a sudden, that signal gets bent just a little bit, and then a little bit more, and then a little bit more, and a little bit more, and pretty soon it's headed away from the charged particles and back toward Earth, and bingo, you have skywave. Whoops. I was talking. So here's a skywave, and you can see part of it is just heading off planet X, and some of it is getting back down to Earth. And in fact, it can come back down to Earth, bounce up, come back down, bounce up, and do that up to 5 times. That's how we get global communication. However, let's say our photon, 20 meters wide, heads up to the ionosphere and finds particles 80 meters apart. Well, that's not going to work. Yes, sir. Exactly. So, density of free electrons up there is what's going to determine the maximum usable frequency. Long space between the electrons means that frequency is going to be really low. Short space, frequency is going to be high. So imagine that I have a beach ball about 2 feet across. You have a really good imagination. Here's my beach ball. That's your signal. You're trying to bounce it off a picket fence, perhaps while you're blindfolded. If the fence's pickets are an inch apart, that ball's going to bounce back every time. But if the pickets are 2 feet apart or 3 feet apart, it's not going to come back nearly as often. You'd need a 4-foot beach ball, which I didn't bring. In other words, a lower frequency radio wave in order to make that signal bounce. So the maximum usable frequency is determined by the free electron density. As we get more free electrons, the MUF goes higher. More free electrons, higher frequencies bounce. So, that must mean that 160 meters is the absolute best frequency for DX, right? Because that's the biggest wave, so that should bounce off the picket fence just great. It's our biggest beach ball. Oh. See, all the top banders are doing this. They don't want to look me in the eye and break the news. Yeah. Before I answer this 160-meter question, something that might at first glance seem like nitpicking, but it's one of those distinctions without a difference, but it's about to become very significant. When we bounce a signal off the ionosphere, we're not really bouncing it like a ping pong ball bounces off a wave or a wall. We're refracting it. It's getting bent back to Earth, and it's being bent back to Earth because it gets absorbed by an electron and then re-radiated by that electron. So effectively, you've moved your transmitting antenna up 100 miles or so above the Earth. Now, there's a rule. In order to absorb and re-radiate your signal, that electron must stay free. It must not rejoin an atom for at least one cycle, the duration of at least one cycle. That's why there is a lowest usable frequency. If the electrons are recombining faster than the length of your signal, one cycle of your signal doesn't get reflected. It gets absorbed. It doesn't get re-radiated. In the upper layers of the ionosphere, free electrons can last for hours, days sometimes. In the lower layers, not so much. If they're close together, all the air molecules are close together, like down there in the D layer, free electrons might only last a microsecond or less. At a microsecond, any frequency under 1 megahertz is too low, and it's guaranteed to get absorbed. Since the 160-meter band starts at 1.8 megahertz, well, any recombination faster than about 2 microseconds is going to eat our signal. Even at a full 2 microseconds, chances are good our signal got there too late for half of those electrons, right? Because they're hanging out for a certain amount of time, so half of them are going to recombine. Of course, anything could happen with any individual electron, but we can calculate the average rate of ionization and recombination for a given layer under given conditions. That is called the plasma frequency. If you read it, in some technical journal, that's what they're talking about. And the plasma frequency, that rate of recombination, that's what determines the LUF, the lowest usable frequency. Longer waves tend to get absorbed more than shorter waves. So let's see how this all stacks up layer by layer. Here's the D layer. We have lots of air molecules, but a lot of the radiation got filtered out on its way through the upper atmosphere, so we don't have a lot of radiation there to create free electrons. And when they get created, there's always an atom nearby, so it can just recombine and eat your signal on the way. At the same time, because of the proximity of those other molecules, the recombination rate is really, really fast. Now here's the E layer. We have fewer air molecules farther apart, also more radiation. So we're getting more free electrons created. Still have a relatively fast rate of recombination. During the day, most of the time, we can't get much of anything through the D layer that can be refracted by the E layer. That adds up to 0 or very limited daytime propagation from the E layer. However, there are times that isolated pockets of very high free electron density occur in the E layer. Then we have possibilities for low VHF, like 10 meters or 6 meters usually. Those frequencies can get through the D layer, and under these conditions can get refracted back by the dense areas in the E layer. That's sporadic E propagation. Lower frequencies won't work in sporadic E because the recombination rate is still too high in the E layer. Finally, there's the F layer. This is our friend. F for friend, get it? The highest region of them all. It's up there where there's barely any atmosphere at all. Now the atmospheric density is really thinned out, the radiation is at its maximum, lots and lots of free electrons get created, and they last a long, long time. This is why the F layer is, with just a little help from solar conditions, rich territory for HF propagation. Plenty of free electrons to refract a wide range of frequencies, and the absorption rate is very, very low. So, the very, very good news about ionospheric propagation, if you haven't heard, is it looks like, I almost hate to say it, don't want to jinx it, but it looks like maybe we're getting a pretty good start on the next solar maximum. There's a chance, pretty good chance, HF propagation is going to get better and better over the next few years. Great time to get your general if you don't have it already. So, what are the techniques to take advantage of this happy circumstance? Well, the most important technique to take advantage of this great propagation, this is highly technical, you may want to take notes. You want to do this. Stay alive long enough for propagation to improve. The next most important, and if you've been a ham for more than 15 minutes, you can guess what I'm about to say, is your antenna. Have the right antenna. You can have the jazziest new HF radio, and that's all well and good, but at the risk of being skinned alive by the radio merchants over in the halls, people have been communicating all over the world for a very long time with equipment even cruder than this wonderful Collins setup here. Having a high-power amplifier is nice too, but unless it's hooked up to the right antenna, it's not much great is going to happen. So the object of the game when it comes to ionospheric DX is to get our signal to encounter lots of long-lasting free electrons up in the F layer. So takeoff angle is very important, and generally the lower the better. If you can see these, I know these monitors are kind of small, but if you can see there's an arrow going straight up, and there's one that's going kind of at a 45-degree angle, and one that's going like it's going straight out toward the horizon. Well, the one going straight up is going to encounter a lot less ionosphere than the one going straight out to the horizon. And so the one going straight out to the horizon is the most likely to get bent back to Earth and result in a QSO, unless you're trying to talk to Planet X. So what antenna will make this miracle happen? How many thousands of dollars should I save up for the magic antenna, the one that, you know, has pink unicorns coming out of it and has 3,000 dB of gain? And what do I need? Good news. That's the radiation pattern of a good old long wire dipole. Cheapest antenna you can possibly lay hands on. Get one mounted right, and that does require some altitude. You've got about, the minus 3 dB lobe is heading out at 15 degrees. That's a pretty good takeoff angle. You have a tough time beating that. The cost for a typical multi-band dipole is in the dozens of dollars, even if you run over to MFJ and buy one of their pre-made ones. You can make it yourself. For those of us without any possibility of getting a dipole up the proper distance in the air, well, there are other possibilities. For me, it's a vertical in my backyard. I have room to string out some kind of short radials, but hey, we make it work. Here's the thing about ham radio that I'm constantly teaching people. Your dipole's not up a full half wavelength? Okay, put it up as high as you can get it. Optimum is not required. Optimum is optional. Any antenna is 100% better than no antenna. Okay? Even if all you do is sit there and get static, you're still having more fun than if you had no antenna at all. So get something up in the air and make it happen. I strongly suspect that if I went out and inspected every single station of every ham in this room, I would find sub-optimum things in every single station. And yet, here you all are, and there's probably lots of awards in here and lots of fun going on and lots of DXing and all kinds of stuff. You're having a great time with ham radio. And your station is not quite perfect. Okay, doesn't require perfect. If you play on the HF bands, I will tell you, your success is going to have a lot more to do with persistence than it is with some miracle equipment. Now, for those with the budget and the space and the commitment, sure. There's the big tower with the big beam antenna at the top, and I want you to be clear. Those are nice to have, but they are not on the need to have list. So my friend who inspired this little book counts more than 200 countries worked and confirmed. He's a double DXCC. He has never in his life touched a radio with more than 100 watts. But 200 countries worked, over 300 worked, but the last 100 haven't confirmed with him yet. So it doesn't take perfect. And John is my friend. His secret, Every time I walk by the radio, I see if anything's happening. And that's how he worked 200 countries. So persistence is everything. Okay, we've gone for however long we've gone, and we've barely even skimmed the surface of the topic of propagation, but I hope I've given you at least a framework to use to think about propagation and to wonder about this stuff. And if you walk away with nothing else, walk away with the notion that there are literally dozens of possible paths to successful communication, no matter what band you're on. And that's my message for you today. Now, we're over in booth 1908, and we have the book there. I have a few copies here if you're interested in our propagation book. They're $15 each, and they're pretty fun. And we're also on the web and all that good stuff. So, thank you all so much for being here and for hanging in here until almost 5 o'clock. Really appreciate that, and enjoy your time at Dayton. Thanks. Oh, and I'm happy to take questions. We do have time for it. So, any questions? Going once, going twice. Come up and ask me afterwards if you want. Thanks, everybody.